Right now, the spacetime beneath your feet may be riddled with holes, not cracks, not damage. Geometry. Tunnels forming and collapsing 10 to the 43 times per second at a scale no instrument on Earth can see. You are sitting on a surface that physics says is anything but solid. This is what we know about wormholes. You will never see one. Not because they're rare, because they die before light can cross them. This is the original wormhole. Einstein and Rosen described it in 1935 as a bridge connecting two separate regions of spacetime through a single throat. For a wormhole containing the mass of the Sun, that throat spans roughly 3 kilometers. Fuller and Wheeler confirmed in 1962 what the math had always implied. It collapses in under 0.001 seconds. Nothing gets through. Not a photon, not a signal, not a single bit of information. It forms and seals itself in less time than it takes your neurons to fire. It is not a door. It is a door that exists for a fraction of a blink, welded shut before you can reach for the handle. Same concept. Less exotic matter. Michael Visser proposed in 1989 a shortcut. Instead of threading exotic matter throughout the entire structure, concentrate it on a single thin layer at the throat. One hypersurface, built by cutting two known spacetimes apart and stitching them together at the edge. The result uses the minimum possible amount of exotic matter while maintaining the throat. Engineers thinking about wormholes, and some do, consider this the most resource-efficient design. It doesn't eliminate the exotic matter requirement. It just makes it a smaller nightmare. The first wormhole built on purpose. Kip Thorne designed this one in 1988 because Carl Sagan asked him mid-novel whether faster-than-light travel was physically defensible. Thorne's answer became a paper. The Morris-Thorne wormhole is spherically symmetric, static, and traversable, held open by exotic matter that violates the null energy condition, meaning it carries negative energy density at the throat. Conservative calculations require exotic matter with negative mass equivalent to Jupiter or larger. The tidal forces across the throat can be tuned to human survivable levels if the throat is wide enough. A traveler stepping through could cross a galaxy in minutes. The light from that destination took billions of years to reach us the conventional way. The exotic matter requirement is not a small engineering problem. Negative mass has never been produced at macroscopic scale. Quantum fields allow tiny violations locally. Jupiter-scale violations are a different question entirely. Electricity changes the geometry. In the Reissner-Nordstrom solution, electric charge bends spacetime differently than mass alone. A charged wormhole introduces repulsive effects at the throat and generates multiple horizons instead of one. Under certain matter configurations, this repulsion can push back against gravitational collapse, the charge itself doing part of the work that exotic matter would otherwise handle. The structure becomes more complex, regions of spacetime layer on top of each other like floors in a building with no stairs between them. The charge doesn't make it traversable automatically. It makes the mathematics harder and the topology more crowded. Angular momentum breaks causality. In 1998, Edward Tejo described a rotating wormhole, axially symmetric, stationary, carrying angular momentum the way a Kerr black hole does. The rotation introduces ergo-regions, zones where spacetime itself is being dragged faster than light can resist. Frame dragging pulls any infalling object sideways before it reaches the throat. The deeper problem is closed time-like curves. paths through spacetime that loop back on themselves. In Teo's solution, the mathematics allows trajectories that return to their own past. Whether this describes actual physics or a failure of the model is unresolved. Time travel paradoxes are not ruled out. They are also not confirmed. The rotating wormhole sits in a region of general relativity, where the equations produce answers that physics cannot currently verify or discard. The floor of reality may be a network of holes. John Wheeler proposed in 1957 that at the Planck scale, 1035 meters, roughly 1020 times smaller than a proton, spacetime doesn't look smooth. It looks like foam. Quantum fluctuations at this scale are violent enough to warp geometry into transient bubbles, tunnels, and connections that form and dissolve 1043 times per second. These micro wormholes are not traversable. They are smaller than any particle and exist for intervals too brief to measure. But if Wheeler was right, the spacetime you're sitting in right now is a seething mesh of geometry constantly tearing and re-knitting itself at a scale no instrument on Earth can see. The chair beneath you is built on a surface that may be riddled with vanishing tunnels. The stability you feel is an emergent property of the chaos below. Two particles, one geometry, no contact required. In 2013, Juan Maldacena and Leonard Susskind published a proposal that reframes quantum entanglement. Their claim, when two particles are entangled, meaning measuring one instantly determines the state of the other regardless of distance, they are not just correlated. They are connected by a microscopic wormhole. ER refers to the Einstein-Rosen bridge. EPR refers to Einstein, Podolsky, and Rosen's 1935 paper on quantum entanglement. The proposal says these two things, derived separately across 78 years, describe the same structure. Every entangled pair in the universe would then be a geometric link, a wormhole too small to traverse, too fundamental to ignore. The Milky Way contains an estimated 1024 stars. The observable universe contains roughly 2 trillion galaxies. Entanglement is happening at every scale, in every atom, in every photon crossing the cosmos right now. If ER equals EPR, spacetime is not a background the universe sits in. It is something the universe's quantum connections are building, pair by pair, moment by moment, not traversable, not confirmed, not denied. Sitting exactly at the place where the two most successful theories in the history of science refuse to agree with each other and have refused for 100 years.